Welcome to this explainer. Today, we're diving straight into the fascinating evolution of computer memory and hardware architecture. We're going to unpack the entire journey, moving from the rigid permanence of read-only memory, or ROM, all the way to the ultimate dynamic flexibility of programmable logic devices. If you've ever wondered how engineers balance fixed physical constraints with totally adaptable logic and circuit design, you are in exactly the right place. Here is our roadmap for today. We'll start with an introduction to ROM, tackle some memory-sized problems, explore programmable logic devices, compare PROM, PAL, and PLA, and finally wrap up with our key takeaways. Let's get into it.
Section 1. Introduction to ROM, or Read-Only Memory.
So, the absolute most crucial thing to remember here is that ROM is quite literally built to hold permanent information. It serves as a fixed, unchanging blueprint for your hardware. When a combinational circuit is implemented using a ROM, that binary information is hardwired directly into the device right on the manufacturing floor. There's no writing capability here for the end user. It's all about permanent, rock-solid retrieval of predefined data.
Take a look at this setup. It's a fundamental block diagram. Simple, but incredibly powerful. You've got K number of inputs acting as your address lines, and those K inputs pinpoint exactly 2 to the power of K different memory locations. Feed it a specific address, and bam, the ROM grabs that exact location and spits out the stored data across N outputs. It's a precise, totally deterministic mapping right from the input address straight to the fixed output data.
Now, while your basic mask-programmed ROM is completely permanent, engineers realized pretty quickly that they needed some wiggle room, especially during the design phase. So they created erasable versions. We have EEPROM, which you can literally erase by blasting the chip with ultraviolet light, super handy for prototyping when you might need to wipe the slate clean a few times. And then we evolved to EEPROM, where you can just use an electrical signal to erase it while it's still in circuit. It trades a little bit of that absolute permanence for a ton of convenience, especially when you need frequent updates.
All right, moving to Section 2, Solving Memory-Sized Problems Using Coincident Decoding.
This brings us to a classic, everyday engineering challenge. Say you need to design the decoding logic for a 4K by 16 memory unit. Doing that with one massive, single decoder? Yeah, that would be completely inefficient in terms of hardware gates. Instead, engineers use something called coincident decoding, which is essentially splitting the internal decoder into an X selection and a Y selection. The big question here is, how do we mathematically figure out the optimal size for these split decoders and calculate exactly how many AND gates we're going to need?
Let's actually break down the math and see how this builds. First up, the total locations. 4K is just 4 times 1024, which gives us exactly 2 to the power of 12 locations. Now, if we tried using a single decoder for those 12 input lines, we'd need a ridiculous 4,096 AND gates. No way. But if we break those 12 input lines into 2 separate 6-line inputs, our X and Y selections, we create 2 6x64 decoders. Since each one only needs 64 AND gates, our total drops to just 128 AND gates. Honestly, it's a massive hardware optimization just by using simple coincident decoding.
Section 3, Programmable Logic, or Configurable Components.
Okay, this concept right here changes absolutely everything. A programmable logic device, or PLD, is an integrated circuit packed with logic components. But here's the kicker. Instead of the manufacturer permanently locking in the logic gates at the factory, you, the user, the engineer in the field, actually get to program the circuit's behavior. This means one single, mass-produced chip can be customized to perform an almost infinite variety of specific digital functions.
You can really see the evolutionary leap here. It represents a massive shift in power straight from the factory into your hands. We aren't bound anymore by whatever was physically burned into the silicon months before we even bought the chip. By utilizing programmable AND arrays and programmable OR arrays, PLDs give us rapid prototyping, super quick corrections, and the ability to build highly complex logical structures that adapt exactly to what we need in the moment.
Section 4. Comparing PLDs, specifically PROM, PAL, and PLA.
Think of this table as your ultimate cheat sheet for combinational PLDs. It perfectly shows how flexibility scales based on how many logic arrays you're actually allowed to tweak. Up top, we have PROM. Think of a PROM as having a fixed AND array, which basically acts as a full decoder, but it gives you a programmable OR array. Because that AND array is fixed, it's the least flexible option. In the middle, the PAL flips the script. It has a programmable AND array, but a fixed OR array, giving you medium flexibility. And finally, the PLA. This is the heavyweight, where both the and the or arrays are completely programmable, granting you maximum design flexibility. If you look at this schematic, you can literally see those structural differences mapped out. Up in diagram A, the PROM is totally locked down on the input side. In diagram B, the PAL gives you the reins on the inputs, but funnels everything into fixed outputs. But look at diagram C, the PLA at the bottom. It's the only architecture where both blocks are shown as programmable. It is a complete dual-layer blank canvas for hardware engineers.
Let's zoom in on the PAL architecture for a second, because it actually presents a really fascinating engineering trade-off. PALs are generally way easier to program than PLAs. But since the OR array is fixed, you hit a unique structural constraint. Product terms absolutely cannot be shared among 2 or more OR gates. Every single output gets its own dedicated set of AND gates. Practically speaking, this means every Boolean function you write has to be independently simplified to fit its specific section. If a function is too complex and needs more terms than you have available, well, you might actually be forced to cascade into a second section just to implement that one single logic function.
And finally, Section 5, Summary and Key Takeaways.
So what does this all mean? The absolute biggest takeaway here is that hardware design is a constant, delicate balancing act. On one end of the spectrum, you've got the absolute rigidity of ROM and fixed decoders, which give you steadfast reliability. But as our systems get more complex, PLDs step in to give the power right back to the user. And exactly how much power you get depends entirely on the architecture, whether you're working with the fixed and constraints of a PROM, the balanced trade-offs of a PAL, or the ultimate, adaptable complexity of a fully programmable PLA.
I'm going to leave you with this thought to ponder. If user-programmed PLDs offer this much incredible flexibility, how is this shift from rigid hardware to adaptable logic going to dictate the future of the smart devices we use every single day? As configurable logic blocks inside massive FPGAs start replacing single-purpose chips, could the devices of tomorrow dynamically rewire themselves on the fly? Thank you for exploring the architecture of logic with me today. Keep questioning, keep learning, and I'll see you in the next explainer.